Today, we're going to peek behind the curtain at one of the most powerful, yet almost totally hidden tools in all of technology. We're going looking for the invisible engine that runs so much of our modern world, and you might be pretty surprised to find out what it is.
So here's a question for you. What do the incredible graphics in your favorite video game, the encryption that keeps your bank account safe, and the models that predict tomorrow's hurricane have in common? I mean, they sound completely unrelated, right? Well, it turns out the answer is exactly the same for all three.
They all run on this, the Matrix. Now, I know what you're thinking, but it's not science fiction. It's actually a surprisingly simple grid of numbers that happens to be the key to solving some of the most complex problems you can imagine. So let's demystify it together. At its heart, a matrix is really nothing more than a box of numbers. Seriously, it's just a rectangular grid, neatly organized into rows that run side to side and columns that go up and down. Every single number inside that box is called an element. That's it. It's not magic, it's just a really smart way to organize information. For example, let's look at this one. It's got 2 rows and 3 columns, so we'd call it a 2x3 matrix. Simple enough. And if you wanted to find the element in, say, the first row and the second column, you just find where they meet, and there it is, the number 7. It's kind of like giving every number its own unique address. And doing math with them is actually way more straightforward than you might think. For example, to add 2 matrices together, there's just one rule. They have to be the exact same size. If they are, you just add the numbers that are in the matching spots. Top left adds to top left, bottom right to bottom right. You get the idea. So see, the basics really aren't that intimidating. Okay, so if they're just these simple grids, where does all this incredible power come from? Well, it turns out their real strength isn't what they are, it's what we do with them. And once you start looking, you'll find them absolutely everywhere, from the phone in your hand to the stars in the sky. In our digital world, matrices are the ultimate puppet masters. A matrix is what tells a computer exactly how to rotate, shrink, or move an object in a video game. They're what allow your phone to recognize your face. They're even the engine behind the audio and video filters we use every single day. They are constantly working, totally silently, in the background. And they are the absolute backbone of our data-driven world. A matrix can hold a massive data set for a machine learning algorithm, and then it can be used to completely scramble or encrypt that same data to keep it safe. They're used to model everything from our social networks to global economic trends. But their reach extends way beyond the digital, right into our physical world. Matrices are used to calculate the stress on a bridge to make sure it's safe. They program the incredibly precise movements of a robotic arm in a factory. They even run the mind-bogglingly complex simulations that predict the weather. Yeah, from your GPS to the buildings downtown, they are the framework. So this is the crucial part. How do they do it? How can a simple grid of numbers solve such gigantic problems? Well, the secret lies in their uncanny ability to take total chaos and turn it into beautiful, simple order. Just imagine you're faced with a problem like this, a whole tangled web of equations. Trying to solve this by hand would be, well, a nightmare. You'd be substituting and rearranging for hours, it'd be super messy, and it would take forever. This right here, this is the chaos. But now watch this. Using matrices, we can take that entire messy system and package it all into one single, clean, beautiful equation. AX equals B. Just like that. All those numbers and variables are perfectly organized. A holds all the coefficients, X holds the unknowns we want to find, and B holds the answers. This is how matrices bring order to chaos. Now, to solve this, we need 2 special tools from our toolkit. The first is called the identity matrix. The easiest way to think about it is that it's just the matrix version of the number 1. You know how multiplying any number by 1 doesn't change it? Well, it's the exact same idea here. Multiplying any matrix by I leaves it completely unchanged. Our second tool is the inverse matrix. And if the identity matrix is like the number 1, the inverse is like reciprocal. You know, like how 1/8 is the reciprocal of 8? When you multiply a matrix by its own inverse, they basically cancel each other out, leaving you with that nice, clean identity matrix. It's the ultimate undo button. So how do we put this all together? We start with our tidy little equation, AX equals B. We want to get X all by itself, right? So we just multiply both sides by our undo button, the inverse of A. And just like that, the solution to that entire chaotic system of equations becomes one incredibly elegant step. X equals A inverse times B. and a computer can solve that in the blink of an eye.
But hold on, because the power of matrices goes even deeper. They don't just solve equations, they actually have a kind of secret code hidden inside them, a code that reveals their most fundamental properties. And this is where we get into something really cool called eigenvalues.
And as this quote suggests, the whole point of this secret code is to cut right through all the complexity. It's a way to see the true, essential nature of what a matrix does without getting bogged down in all the messy numbers and calculations. So what is this code? It's made of two parts, eigenvalues and eigenvectors. Just think of a vector as an arrow pointing in a specific direction. Now, if you multiply most of these arrows by a matrix, they get knocked off course. They end up pointing somewhere completely new. But eigenvectors, they're special. When a matrix hits an eigenvector, it doesn't change direction. It stays on the exact same line. It only gets stretched or shrunk. And that amount it gets stretched, that's its eigenvalue. Take a look here. See how that eigenvector x stays perfectly on its line after it's been multiplied by the matrix A? It's not pointing somewhere new. It's just been scaled, in this case, stretched out. The eigenvalue is the number that tells us exactly how much it was scaled. In a way, these special vectors reveal the true fundamental directions along which a matrix shows its power. Okay, but why does finding these special directions even matter? Because, and this is incredible, eigenvalues can basically tell the future. An eigenvalue of 1 points to what's called a steady state, a part of the system that's going to stay stable over time. An eigenvalue less than 1 reveals a decaying mode, something that's going to shrink and eventually disappear. This is how we can predict everything from population changes to whether a complex system will stay stable or fall apart.
So how did we even get here? I mean, this incredibly powerful tool wasn't just invented overnight. It has a really fascinating history, slowly evolving from a pure mathematical curiosity into the absolute cornerstone of our digital age.
The very first seeds were planted way back in the 17th century, but it wasn't until the mid-1800s that the term matrix was even coined. And it comes from the Latin word for womb, as in a place where things are formed. How cool is that? Then Arthur Cayley came along and developed the algebra, the rules for how to work with them. But the true explosion happened with the computer age, when pioneers like Alan Turing realized matrices were the perfect tool for digital computation. And you can see that journey right here. The whole thing started slow, then all of a sudden it took off. What began as just a pure theory for mathematicians eventually found a home in physics. But it was the dawn of computing that just caused an absolute explosion. The number of applications grew exponentially, making the matrix an essential cornerstone of pretty much all of modern science and technology. And that brings us to one final thought. The story of the matrix is nowhere near finished. As our world gets more and more complex and our computers get more and more powerful, this invisible engine will only become more essential. So the real question we have to ask is, what new incredibly complex systems will this simple grid of numbers help us understand and build next?